Alright guys, so here is what should be the last trig video before the first trig test. So we're going to be talking about the different formula for the half angles. And so here's a brief rundown of the two angle formulas that we do have right now. On top we have the sum formula, and in the lower left hand corner we have the double angle formulas. And remember, if you have to memorize only one formula for the entire section, this is it. These two formula literally give you everything, right? If we take these two formula and you let theta replace alpha and beta, you get all of the formulas down here on the left. Every single one of these comes from the formula up top, and also using the sine squared plus cosine squared equals one formula, right? So if you take the top two formulas into consideration, you can get a lot of formulas for free. What we're going to do today is we're going to take these two formula and we're going to massage them to give us formula for the half angles instead of the double angles. And so here's how we do it. If you just follow down the left side, starting with cosine of 2 theta equals 1 minus 2 sine squared theta, you just get sine squared by itself by adding sine squared to both sides, subtracting cosine 2 theta from both sides. That gets you to here. And then divide both sides by 2. Gets you to here. And then when you take the square root of both sides, you can see this tricky thing that has to happen where we leave the plus minus, and the reason for that is the square principle always tells us that if you have down at the bottom here a squared equal to b, then that means a has to equal plus or minus radical b. And so we use the square principle and we get that sine theta equals plus or minus 1 minus cosine 2 theta over 2. And if you look back, we have these double angle formulas. We're taking sine of double angles and replacing it with the angles we know. Here, likewise, we're going to want to take sine of half angles. And so to do that, we just replace both of the thetas, right? This theta and this theta. We're going to replace them with theta over 2. And then we get our final answer for sine of theta over 2. And over here on the right hand side, starting instead with 2 cosine squared minus 1, and working our way down, we get a formula for cosine of theta over 2. And you can see that they're basically the same two formula, right? It's always 1 plus or minus cosine of theta over 2, and then you take the square root, and then there's a plus or minus out front. Now, let me just say a couple of things. The plus or minus is never in your final answer. That if you know the angle, you can figure out if it's going to be a plus or if it's going to be a minus. And that's because we know the sort of all students take calculus trick as to which quadrant we're in will determine what the value is. And so let's look at one of these in action. So here's evaluate sine of pi over 8. Remember, our sine formula has the minus, and so sine theta over 2 is plus or minus the square root of 1 minus cosine theta over 2. And so here, pi over 8 is our theta over 2, and so pi over 4 is our theta. And this is great because that's something we know what to do with. Also, pi over 8 is in quadrant 1. And so when we try to take sine of pi over 8 and we replace it with the square root of 1 minus cosine pi over 4 all over 2. Because pi over 8 is in quadrant 1, sine of pi over 8 should be positive, and so we pick the positive. And so now we just have to evaluate. And so that's equal to the square root of 1 minus, now the cosine of pi over 4 is rad 2 over 2, all over 2. And now we like to simplify when possible. And so I'm going to multiply top and bottom by 2. And what I'm going to get is the square root of 2 minus radical 2. And on the bottom it's 2 times 2, which becomes just 2 after we take the square root. And so here's our final answer. Radical 2 minus radical 2 over 2. And that's it. And remember, the reason it's positive is because pi over 8 is in the first quadrant, and so sine of pi over 8 should be positive. Let's evaluate cosine of 17 pi over 2. So again here, our theta over 2 is the 17 pi over 12, and so our theta is 17 pi over 6. Now, there's 0, there's pi. If I was to do this in twelfths, that would be 12 pi over 12. Here'd be 18 pi over 12. And so my angle is somewhere down here. And so that's in quadrant 3. And so cosine is negative, right? All students take calculus. Only tangent is positive there. And so this is going to be negative. And let me go ahead and make some more room there. We have cosine of theta over 2 is plus or minus the square root of 1 plus cosine of 2 theta all over 2. And so cosine of 17 pi over 12 is, for us, remember it's negative, so we keep only the negative sign, 1 plus cosine of 17 pi over 6 over 2. Now, where is 17 pi over 6? Well, we have 6 pi over 6. We have 12 pi over 6. We have 18 pi over 6. So 17 pi over 6 is right here. And so we are pi over 6 away from our 18 pi over 6. And so our reference angle is pi over 6. Remember, cosine is negative in quadrant 2, right? So this requires a whole bunch of our skills. 17 pi over 6 is here in quadrant 2. We need to replace 17 pi over 6 with its reference angle, which is pi over 6. But when we do that, we have to switch the sign on cosine to negative because we're in quadrant 2. So watch what happens. This is negative the square root of 1, and we're going to replace cosine of 17 pi over 6 with cosine of pi over 6, but instead of a positive, we need that negative now, and that's because we're in quadrant 2, and to use the reference angle you have to fix the sign all over 2. Now cosine of pi over 6 is 1 minus radical 3 over 2 over 2. And so now when we go to clean this up, and we multiply under the radical by a 2 up top and another 2 down below, what we get is the square root of 2 minus radical 3 all over 2. We have that negative outside. And so there is cosine of 17 pi over 12. So let's do one that requires extra work. So here we have cosine of pi over 16. The reason this requires extra work is that our theta over 2 is pi over 16, but our theta is pi over 8. And that means we're going to have to do the half angle formula twice because pi over 8 still isn't good enough. And so cosine of pi over 16 is, now remember, pi over 16 is here in quadrant 1, right? Pi over 16 is very tiny, so it's very close to 0, so it's still here in quadrant 1, so we're going to have the plus, we're going to have the positive square root of 1 plus cosine of pi over 8 over 2. Now over here, cosine of pi over 8 is the positive square root of 1 plus cosine of pi over 4 over 2, which is the square root of 1 plus rad 2 over 2 over 2, which is the square root of 2 plus radical 2 all over 2. So this is cosine of pi over 8, so we can now plug that into our other formula here. So we have 1 plus the square root of 2 plus rad 2 over 2 all over 2. So let's multiply top and bottom by 2. And what we get is the square root of 2 plus the square root of 2 plus the square root of 2 all over 2. And so I bet you can figure out a way to keep getting more and more square roots of 2 embedded into a pattern like this. If we took cosine of pi over 32 or pi over 64, we could keep this going on forever. So here's my pro tip. Whenever you wish to double an angle, that's when you use the half angle formula. It sort of seems the opposite of what you want. If the angle you have isn't workable, but double the angle you have is usable, and it's something you know the cosine or sine for, please use the half angle formulas. That's the time to use it. Now we've been doing a lot of work with different quadrants, and so here's one that involves solving a triangle. So suppose cosine of theta is 3/4, and theta is in quadrant 4. What is sine of theta over 2? So you don't know the angle now, but we do know that sine of theta over 2 is plus or minus the square root of 1 minus cosine theta over 2. So here's a chance for us to do some work. So we know theta is in quadrant 4, which means theta is between 2 pi and 3 pi over 2. So where's theta over 2? Well, that's between pi and 3 pi over 4. That means it's between these two angles. And here, ASTC, sine is positive. Since sine is positive, we're only going to keep the positive root. And so we can go ahead and do this. Sine of theta over 2 is the square root of 1 minus 3/4 over 2, and the reason I use 3/4 is because that's what cosine of theta is. And so we get, this is 1/4 over 2, which is the square root of 1/8, which is radical 8 over 8, which is radical 2 over 4. And you can do the work on reducing that yourself. And so that's the half-angle formula for whatever angle in quadrant 4 gives us cosine theta equals 3/4. And there's our final answer. Lastly, we've been doing a lot of identities, right? And so let's use the half-angle identities to show that 2 sine of theta over 2 cosine theta over 2 equals sine theta. And so we get 2 times the square root of 1 minus cosine theta over 2 times the square root of 1 plus cosine theta over 2, which is, well, radical 2 times radical 2 is, when we multiply these two, we're going to get 4 underneath the radical, which will become 2 outside the radical in the denominator, and that 2 will cancel with the 2 outside, so these will cancel with that. And so we're left with 1 minus cosine theta times 1 plus cosine theta, which is 1 minus cosine squared of theta. And 1 minus cosine squared is just sine squared of theta. So we get sine theta when we take the square root. Now, there's a couple of things that I've ignored here. One is the fact that there's all these plus or minuses flying around. And so at the end of the day, you still have a plus or minus flying around, and then you get a plus or a minus. You technically get the absolute value of sine theta when you take the square root of a square, but if you do a bunch of checking for possible thetas and theta over 2's, you can see that this will actually all reduce to exactly the same sign as sine of theta, and the first sign means the plus or minus kind, as opposed to the second sign, which means the sine function. And so there's a half-angle identity formula to check. And so that's it. So remember, use the half-angle identities whenever you want to double an angle, as opposed to using the double angle identities whenever you want to replace an angle with half of an angle. And so that's really all I have to say. Go ahead and do the homework, and I will see you in class.